In the last session of this ephemeral architecture video course, we are going to talk about catenary structure or compression structures. These are mainly used for building or designing and building architectural ephemeral pavilions. You might have seen many during the last years. But they are all based on one basic principle, which was already used by, for example, the architect Antonin Gaudí for the design of, well, basically many of his masterpieces. So first of all let's understand what's the catenary curve. Many people when they see this kind of curve, they think about a parabola curve, but actually this is not a parabola. This is exactly a catenary, which is a different type of curve. It is called like this because it basically takes the shape of a chain falling under its own weight, being anchored at the endpoints. We can easily see that this catenary curve is not a parabola. Just doing a very quick drawing, I can use a range component with a graph mapper. The graph mapper also has a parabola graphic here, so I can create a series of points where the x is basically defined by the range values here, and then what I'm going to do here is switch to the front viewport, because catenary curves normally are generated in a vertical plane because they fall due to gravity. Okay, so we must consider the z vertical direction if you want to see these curves in action. So I will construct this point using the range as x coordinate and the graph mapper results as z coordinates. So you can see that this is actually a parabola. I will also use an interpolate curve in order to see this curve. Okay. So now I have this curve here. I will calculate the endpoints. And then I would use these points to construct a catenary curve. You see that there is also a standard Grasshopper function. You can find it in a curve, spline, and catenary here. We need the start point and end point. We already have them. And then this function here asks for the length. And it says it should be larger than the distance AB. Of course, if you want this curve to bend due to gravity, well, the length of the curve must be larger than the distance between its start point and end point, else we will get a straight segment. Okay, so what I'm going to do right now is define the length using a particular method. I'm going to calculate the distance between point A and point B, and I'm going to multiply this distance here by a length factor, which will be basically between 1 and, let's say, 5. Okay, so if I multiply the distance by 1, I will get exactly the same value of the distance. So this catenary curve will result in a straight segment. Okay, but if I start to increase this, you see that the catenary starts to fall due to the increment in its length. Okay, so take a look at what happens when this catenary starts falling and reaching the same height or the same depth of this parabola curve. Okay, so you can see that the shape of the catenary looks like a little more fat than the parabola. Okay, so as you can see, there is a slight difference between these two curves. Okay, so don't make confusion between the two, because the catenary is somehow more important. Actually, in my whole life, I think I have never used a parabola for my drawings. Okay, so this is how a catenary curve works. Now, why is the catenary so important? Because if we take a look, well, let's hide the parabola and the endpoints, okay? So if we take a look at this curve here, actually, as this, the shape of the curve is determined only by the weight of the curve itself. So it's only affected by gravity, okay? What happens to this curve? Why this shape is so important? Because each particle of the curve is actually resisting to falling because of the tension that's being generated all along the path of the curve. So it means basically that if we take this curve here and flip it, so if I take the catenary and say that gravity, instead of being a vector like 0, 0, minus 1, which is basically vertically oriented downward, we can take a vector like 0, 0, 1. So it always means vertically, but this time gravity will be like flipped, so the curve will fall upwards. Now, this is something that of course you cannot do in the real world. That's why, for example, architect Antoni Gaudí was using mirrors on the floor in order to see what the structure of his building would look like in once built. But with a computer, we can simply reverse the gravity vector, so the object starts to fall upward. And that's what's happening here with this curve. Now, if the curve falls down and it's subject to pure tension, when it falls up, it will be subject to pure compression. So it means that all the particles of these curves are actually compressed. Okay, so it means that in this case, for example, this catenary is only falling because of its weight or self-weight. But imagine that if we apply a uniform load over the curve, the catenary curve will fall a little more. It means that if you flip it and you apply the same load that you have applied for having the catenary falling down, the catenary structure could resist exactly the same load in real life. And this is exactly what we are going to do in our examples. Okay. Now the problem is that mathematically this is basically pretty straightforward. Each particle of the curve is subject to compression in this case. But if you think about computer calculation, saying that each particle of this line is subject to compression, it means that in order to calculate the stress inside this curve, we should perform an infinite amount of calculation, because there is an infinite amount of points along this line. Okay, so that's why when we use a plugin in this third section, which is Kangaroo, and we simulate this physical behavior with some, let's say, simplification of the system. Okay, so first of all, let's build the first system. So basically it will be a catenary curve. You see that there are a bunch of pre-made scripts here. I will, as always, start from scratch so that you will follow exactly all the process. Okay, so let's create a real catenary, not like this one, which is basically a static curve. I want to create a catenary that actually reacts to some physical actions. Okay, so in order to create a catenary, there is a particular method that we must follow in Grasshopper and Kangaroo. So I will create 2-point container and set 1 point each. Let me deactivate grid snap and set 1 point also for the second container, and therefore I will create a line. Okay, so now this line is made up of one single segment. Okay, and the abstraction or the simplification that we are going to do in our Kangaroo simulation is this. Straight segments are basically springs. Okay, and they are ideal springs. I don't know if you remember something about your studies in physics eventually at university, but an ideal spring is an element that can only extend or contract. Okay, it cannot bend. So basically, this ideal spring can only stretch. Okay. Now, if we consider this line made of one single segment, and this segment is anchored at the endpoints, it means that even if we apply a vertical load along this segment, this line will not be able to bend because it will be one single ideal spring. Okay, so in order to have this line falling down according to the action of gravity force, we must simulate, or we must, let's say, change the nature of this segment and convert it into a chain of segments, so a chain of springs. Okay, so in order to do this, I'm going to use the shatter command, which takes a line and splits it into segments according to the value of a parameter. Okay, now this has to deal with parametric representation of NURBS geometry. I will simply take a range component, which is outputting a series of progressive number between 0 and 1 with a regular step, and I will use it in order to split this curve. Now, remember always that when you work with parametric representation of NURBS geometry, even if some components automatically recognize this situation, I always recommend that you reparameterize the geometry in order for these components to work properly. Okay, so reparameterize means that it doesn't matter what is the geometrical length or geometrical dimension of the NURBS geometry. When you reparameterize it, this span will measure exactly 1. So it means basically that the parameter will flow from 0, which is the value for the start point, and 1, which is the value for the end point. And therefore, if we define these parameters t using a range, the range will output 0, 0, 1, 0, 2, 0, 3, and so on. So we will be splitting this line into 10 segments which have all the same length. Okay. Now, the only problem with shatter is that the shatter doesn't visualize the division point. Okay, so you will only get segments here. We can eventually visualize this using a dispatch command and send half segments into A and half segment into B. They are not yet visible because dispatch has a preview that includes both A and B. But if I take a curved container now, you can see that these are the odd segments and these are the even segments, so 5 and 5. So shatter is working properly. Okay, so these are the 10 segments that will be representing our rope, let's call it so. Remember that we are working in the XZ plane because we are going to use gravity right now. So these segments here must be converted into ideal springs, okay, and must be passed to Kangaroo for calculation. Now, normally, I would recommend you start approaching physical simulation with Kangaroo using the older version of Kangaroo. Kangaroo exists now in 2 versions. The most recent one is Kangaroo 2, which is this one. But there is also the old Kangaroo, which is not Kangaroo 1, is Kangaroo 0.99. Don't ask me why. But I would recommend that you start working with Kangaroo using the 0.99 version because from a let's say from the learner point of view, I would say is much detailed. Okay, Kangaroo 2 is somehow a simplification from my point of view of the older version. Okay, but anyway, I will simply skip this in my opinion, necessary step, and I will simply go straight to Kangaroo 2 in order for you to don't have eventually to install the older version and so on. Just open Grasshopper, especially if you're working with Rhino 6, which include Grasshopper, and Kangaroo 2 is already included in Grasshopper for Rhino 6. So you will have everything set for your Kangaroo workflow. Okay, so in this case, what we need to do is convert these segments into springs. Now, there are no springs actually in Kangaroo 2, which is the main difference between Kangaroo 2 and Kangaroo 1. You won't find springs here. but you will find goals. And goals are divided into categories that correspond either to geometry or to specific boundary conditions and forces and so on. So in this case, these are lines, and we are going to goals line. And basically a spring is a strength that affects the length of the line. Okay, so the equivalent of the old Kangaroo 099 springs is the length line component in Kangaroo 2. Okay, so I will say that all the segments here are the lines for which we want to specify the physical properties. So this is the component that converts the segments into springs. Okay. Also, one condition that we must assure now is that this rope is going to be anchored in the start and end point. And these are a different type of geometry, of course. They are points, so we are going into the goals point group, and we will find the anchor component. And anchor only asks for what are the points that you want to anchor, and they are first and second point. Okay, so we have anchor points set, length line, which is elastic property, already set in this length line component, and we miss gravity. Okay, so we must apply gravity to this line. Now, springs or elastic force is applied to segments, while gravity is a force that's applied to points. And now we need to apply gravity to all along the line. Okay, but we don't have actually points along the line. We only have segments. Okay, so we need points. And what I'm going to do, I'm going to use an evaluate curve, where I'm going to evaluate this curve at certain parameters. So once again, as with shader, I am going to use a parametric representation of NURBS line. So I'm going to reparameterize this curve, and I'm going to use exactly the same range that I have here. So you see that now we have points along this line. Okay, and I will use these points here in order to apply gravity to them. And gravity is a force that's applied exactly to points. So we will find it into goals point once again, and it's called load. Okay, so load asks for the point where you want to apply gravity, and it's applied to all these points here. And it also has another input which is important, which is FV, which is force vector. And force vector, as you can see, is 0, 0, 1. So it's vertical because its only component, non-null component, is 1, but it's positive 1. So it means that this gravity will be oriented upward in our coordinate system, which is not actually a problem for us, because we want to have catenary structures falling, let's say so, upwards. But in this case, what I'm going to do, I'm going to simulate this rope hanging from the endpoints. So I want to recover with a real life situation where vertical gravity is oriented downwards. So I will take a unit z vector, and I will say that its factor is -1. And so this will be 0, 0, -1. Okay, so we also have gravity. And I will hide the points here. I will also hide the initial start and end point. I do recommend that when you work with Kangaroo, there is no need to visualize the original geometry. It might be confusing because as soon as we implement Kangaroo simulation, you will see that all the geometry will be shown by the Kangaroo components. Okay, so now we need to calculate this physical simulation. And so we go into the main group in Kangaroo, and we grab one of the solvers. I do recommend normally that you use the bouncy solver, because bouncy solver is a solver that shows you all the iterations of your Kangaroo simulation. Okay, and one important recommendation before connecting anything to the goal objects are any force that's being used in your definition. Okay, so all these three components will be connected into the goal objects input. Before doing this, I do recommend that you do this. Take a Boolean toggle. I do recommend that you also use the false start toggle. if you don't have it, I will share the link for downloading this plugin, which is quite important, in the description of this video. And set it to false and plug it into the on input of your bouncy solver. This means that the simulation won't start until you change this button to true. Okay, so now I will start plugging these components here into the goal objects input. Goal objects ask for 3 data sets, so there is no need to flatten or graft anything here. You just simply plug any of the goals that you have been implementing into the goal objects. Okay, and also one thing that you might want to do is use a button here for resetting the simulation. Okay, so there are these 2 objects here, which are controllers, general controllers for your simulation, and here you have the goals set into the goal objects. Okay, so once you have this simulation set, I would always recommend that you reset simulation before executing it, and then you switch this button, this toggle, to true, and you see that your system starts to fall down. Now I won't go too deep into this elastic forces simulation. There are so many things to comment and observe, but just one observation, which is one of the main questions that every new Catenary users ask is this one. So we have taken a line and divided this line into 10 springs. Okay, and we see that this line falls down and reaches basically this height. Okay, now let's stop the simulation, reset it, and what I'm going to do, I'm going to increase the amount of division for this line. So I'm going to change the step of this range component, which is actually set to 10. I'm going to set this slider to 20. Okay, so we will have, you see that there is some weird representation here, that this is a typical situation provoked by the fact that the button, the reset, has not been hit. So hit this button and you see that everything comes back to normal. Okay, so now we have much more springs here. Each spring can extend once we apply gravity to this rope, and gravity is being applied to more points. Okay, so once we release the simulation, you see that the same rope with the same elastic property and the same gravity applied is falling down deeper than the previous example. Now this should not be possible in real life. Let's say that we have a continuous material, so there is no segmentation. Okay, so what we are doing here is creating a simulation that basically depends on the resolution of the system. This is not acceptable. Okay, but also keep in mind that this is due to one particular situation, and this situation is that each goal that we have been using has a strength. Okay, now take a look at this. We have anchor points that must remain fixed during the simulation. Okay, and their strength is set by default to 10,000. Okay, while length line, which is the elastic force for our rope, is set to 10, and gravity is set to -1. Now -1, 10, 10,000 what? Okay, because normally we should be working with real strength or realistic strength. Okay, so few consideration. I repeat, I won't go too deep in this topic, but it's very important that you understand that the simulation that we are running is proportional to the real life scenario. Okay, so you can think about this simulation as a general behavior that would happen to this body under certain circumstances. Of course, this body eventually will not deform like this, but its deformation would be proportional according to a scale factor if compared to the visualization that we are getting here. Now, how can we get to a realistic simulation? Well, if we want realistic simulation, we must work with realistic parameters. Okay, so first of all, if you are drawing an architectural pavilion, you should work eventually in meters, not because it is the standard unit for drawing architectural projects. You can work with whatever unit you feel more comfortable, meters, centimeters, millimeters, and so on. But because forces are normally expressed in the metric system using meters as length unit. Okay, so if you want to use Kangaroo for a physically correct simulation, you must work with meters in Rhino. Okay, and if you want work in meters, it means that this rope is actually measuring 1, 2, 3, 4, 5, 6.5 meters more or less. Okay. So once you understand this, you are capable of creating a well-proportioned architectural body here in Rhino. Now, let's switch to Grasshopper. Gravity is not -1. Gravity is -9.81 eventually. Okay, so this parameter here, this value here must be set to the proper value for gravity. Okay, but the more important thing is elastic force. Okay, so basically, elastic force takes into account what material we are using in our simulation. Okay, basically all materials are elastic. Okay, and if you want to know what's the elastic force of a specific material, you can Google it, for example, and you will find that each material elastic property depends on one value, one coefficient, which is called the Young modulus. Okay, so you must find the Young modulus and must find the formula for converting the Young modulus into the elastic strength for this component. Now the problem is that strength for a realistic material normally ranges between something like 10,000, for example, and can reach very high values like 200,000, 300,000, and so on. Okay, and why we are not going to do this? Because in that case, the simulation becomes extremely slow. Okay, so yes, it is possible to perform a realistic simulation, physical simulation with Kangaroo, keeping taking into account real properties for materials, but the simulation becomes extremely slow. And of course, if you set the elastic strength to 200,000, for example, you also must adjust the strength of the anchor point, else the elastic property will be so strong that anchor points will start to move around. Okay, so in my website you will find also a Grasshopper definition for using real life strength, elastic strength for a given material. There is basically, the definition works already for something like 20 different materials. And I will share the link to this post in the description of this video. Okay, but anyway, behind this simulation, you see how many theory you must take into account. I will leave this to 10, and I will reset and run the simulation again. So this is the catenary shape that we get using Kangaroo applied to a straight segment. Okay, so the difference between this and the previous catenary curve is that this is a static curve, which shape only depends on the length that we specify, while here the catenary shape depends on the elastic properties of the material that we are using and on the load that we are applying. Okay, so having said that, I will stop the simulation, reset it, turn off the line, and just group and turn off all this definition. So you see that this is actually what's happening here. It's absolutely the same thing. Okay, with some more explanation. Now, of course, we want to work with three-dimensional objects, because ephemeral pavilion or compression structure are three-dimensional objects. But first we must understand another important concept regarding kangaroo. Okay, so what I'm going to do now, I'm going to create a different system made up of linear segments. So what I'm going to do, I'm going to draw here in Rhino a set of line like this and this, and from midpoint to midpoint. So what I want to do, I want the three ropes to fall upward this time, and I want the system to be anchored to the ground just in the endpoints of the first line and the second line. So I want this endpoint, and this to be anchor point, while I want the endpoints of this middle line to be anchored to the midpoint of the first and the second curve. So we should come up with something like, let's say that this is the first line here, this is the middle line, this is the third line. Okay, so what I want to achieve is this line falling upward, this falling upward, and this one should do something like this. Okay, so let's import this line. I will use a curve container, and I will take, first of all, let's keep this line separated for now. Then eventually we will see if we can easily simplify this definition by grouping into a data set. So what I'm going to do, you see that normally, especially when I start working with a new system, I tend to keep components organized according to the distribution, the geometry distribution in the Rhino scene. Okay, just in order to recognize the element more quickly. Okay, so basically what we need to do is to convert these three ropes into three elastic cords. Okay, so what I'm going to do is exactly the same thing that we already did a while ago. So I'm going to shatter this line, reparameterize, and use the range. Okay, so now we have our segments here, and I'm going to use one single range for all the curves. So I'm going to also repeat this, and I'm going to repeat this. So we have the three sets of segments for our three initial curves. Okay, and I want to convert all of these three series of segments into elastic segments. So I go into goals line, take length line. Now I don't care about differentiating the elastic properties of the three ropes. I will just convert all of them into the same, using the same elastic properties. Okay, so they will be basically three ropes of the same material. Okay, so the elastic part is already set. Now we need to apply gravity. So it's a gold point load. We need points along this line. Okay, so I will take a evaluate curve, where I take these lines here, 1, 2, and 3. Remember to reparameterize, because this is a parametric component, and I'm going to use the same shader to convert or to interpolate the points, the evaluation point of this line, and I'm going to apply gravity to all of them. Now I won't change in this case the FV direction. I want these ropes to fall upward. So we have elastic property, gravity. We only need the anchor points, so I will take the end points command for line on the left and line on the right, and I want to convert all these points here into anchor point. So start and end will all be anchor points for our system. Let me internalize data so I can get rid of these three lines in Rhino. And now we only miss the kangaroo bouncy solver with the toggle or false start toggle, and the button set into the reset input. And then we start plugging the anchor points. You see that as soon as you plug the forces or goal objects inside the bouncy solver, you start seeing the corresponding geometry. Okay, the springs and gravity. And then we reset and run the simulation. And you see that we already have our catenary system falling upward. Now, let's stop the simulation and reset it. Okay, and I will recover. Let me turn off the preview of this, undo the delete of these three objects here. What I'm going to do, I'm going to delete the center line, because I want a new center line or new middle line starting from near here, the first curve, and near the second curve. Okay, and so I will have the first line will stay the same, the third one also, but the second, the middle line, will change set one curve to this new curve. Okay, now I internalize this and I delete them. So let's see what happens now to this system when we reset the simulation, okay, like this, and we run it. Let me move forward and whoops, you see that the third line is falling upward and keeps on falling upward because there is nothing to retain its fall. Okay, now why is this happening? This is happening because the endpoints of this center line here are touching the first and third line, but not in a particle. Okay, so if we take a look at this, you see that the endpoint of this middle line is touching the third line along one of the ideal springs. Now, objects in Kangaroo are kept together only if they connect with correspondence to one of the particles, and particles are these points here. The points that you see when you turn on the preview of the bouncy solver, these points are Kangaroo particles, and objects must connect in particles if you want them to stay together. Okay, so let me recover the initial configuration. Why the initial configuration was working? Because this center line connects to the midpoint of the first and of the third line, and the midpoint corresponds to a particle because each of these lines here is being divided into 10 segments. So 5 segments on one side and 5 on the other side, and we have one particle in the midpoint of each of these lines. Okay, so if I set one curve and take this once again and reset, in this case the system is kept together because the midline is touching the midpoint of the first and third line. Of course, this is not guaranteed that the system will work forever, because if we take the range, which is basically defining the amount of segments, the amount of division for this line, and set this range to, let's say, an 11 slider like this, and we reset, now you see that we have 11 segments and 11 segments for the side lines. So the midline is touching the first line and the third one along one ideal spring. So there is no connection in this particle or in this particle. Okay, so even if the line is touching the midpoint and I fire the simulation, it will simply fly away. Okay, so pay attention to when you set up your Kangaroo system. If in this case, for example, as we are using the midpoint, the number of steps cannot be odd. It must be even numbers. So I go into this slider here and say you can only give me even numbers. Okay, so now I can increase the resolution of my system. It doesn't matter how much I increase that value. Eventually I will have a proportional simulation which will have more elasticity, as you can see, but the system will be kept together because all the elements connect in one particle. Okay, so basically you can build any system, however complex it might be. The important thing is pay attention to the connection between the elements. Okay, so let's reset these. I will internalize once again this mid line here. Of course, this definition can be more elegant. Instead of using a three curve container, we could also use just one and so on, but this is just for understanding how Kangaroo works. Okay, so let me organize things a little and let me group and disable this definition. Okay, so now I will eventually change the color of these groups because it's like if they are some generic initial consideration. Okay, so let's give them a yellow color like this. And now let's move forward. We can get rid of these lines and let's switch to a three-dimensional structure, real three-dimensional structure made up of surfaces. Now the behavior and the theory is absolutely identical. Okay, the only difference, the only thing that we must take into account is that Kangaroo cannot work with NURBS surfaces. Okay, why? Because NURBS surfaces are mathematical objects. Okay, they are continuous objects. So one NURBS surface is made up of infinite by infinite amount of points, of particles. It's like considering a continuous catenary curve or a catenary curve made up of a discrete number of segments. So as for the NURBS curve, where we had to shatter the curve and work with a finite set of segments, when we are working with three-dimensional object, instead of working with NURBS surfaces, we must work with meshes. Okay, so of course the speed with which Kangaroo can calculate the deformation and simulation of one mesh depends on the mesh resolution. So the higher the resolution, the slower will be Kangaroo computation. Okay. So initially, what I will do is work with a mesh, a low-resolution mesh, in order to have Kangaroo performing all its calculation very quickly, and then eventually we will increase the resolution so to have a better result. Okay. So let's create a very simple system for now. I will use, well, actually, even in this case, I would recommend that you install the old version of Kangaroo, not only because of the behavior of forces and classification of forces, but also because there are some utilities that you might want to use in your Kangaroo workflow. Now, I won't go deep into this subject, but for example, one thing that you might want to use in your workflow in order to simplify things a little or speed up things a little is this utility here, which is called quad divide, that takes a quadrilateral face of one mesh and divides it into 4 quadrilateral meshes. Okay, so I'm going to use a different method because I'm not sure that you have Kangaroo 099 installed. Okay, but in case you do, you might also try another solution, taking a simple mesh and using the quad divide and see how it increases the resolution of your mesh. Now, I'm not sure you have it, so what I'm going to do, I'm going to create a plane surface. I don't care about the size actually, even if considering what we have said, this should be measuring 20 by 20 meters. Okay, even if I am working with millimeters, but we are not taking into account real life forces or real life dimensions. We are just experimenting a little with Kangaroo. So this plane surface will be my initial system. Kangaroo cannot work with this, so I have to convert this using a mesh surface command. And now you see that I have the mesh visible with its quad faces. The amount of faces is determined by the U and V parameters. So I can define the resolution of my mesh using a slider here and, well, a couple of sliders here. So now I have a 400 polygons mesh. So remember that it's very easy to reach higher resolutions using the mesh surface because these two values here are being multiplied by each other. So 20 by 20 is already a mesh with 400 faces, as you can see. So in this moment, I will lower this to 5 by 5, which is, by the way, the default values for U and B in mesh surface. So I have a 25 polygon mesh, and they are quads. Okay. So this is the mesh that we are going to use for our kangaroo simulation, and basically it's like with lines or curves. Okay. So what we are going to do now, as this is a mesh, is not a line anymore. We are going to the goals mesh, and we must give this mesh elastic properties. And as there was a length line, here we have the edge lengths for our mesh. Okay, so I take this mesh and give it elastic properties using edge lengths. Okay. Also, we must apply gravity to this mesh object. Now, we don't have any points here, and we should eventually extrapolate all the vertices of our mesh, which is something that, by the way, it's possible because we can use the deconstruct mesh component, and this gives access to all the vertices, and we could eventually use the goals point load in order to apply gravity to this mesh. But you can also go into goals mesh, and if you want to apply gravity to the mesh instantly, you can use the vertex loads. So vertex loads apply equal vertical loads to all vertices of a mesh without having to, let's say, visualize them or extrapolate them from the original mesh. So this command does all the work for us. Okay, and automatically you see that the strength is set to minus 0.1. It means that the gravity is oriented downward, as it should be. But we don't want this object to fall down. We want this to be an architectural ephemeral pavilion with a compression structure. So we want the gravity to be positive. And so I would say that this is going to be plus 0.1. As you can see, there is no need to define the orientation, like the directions, like z vector, for example, because this is a component that applies equal vertical loads. So while point load uses a force vector that can have any orientation because it is defined by x, y, and z component, the vertex load only works for vertical actions. Okay, so vertical downwards or upwards. Last thing that we need are the anchor points. Now I'm going to use the 4 vertices as anchor points. Even in this case, this utility was transferred to the new version of Kangaroo. You can go into the mesh group and look for mesh corners. Okay, so mesh corners, what this component do is take the mesh, and according to an angle defined in radians, by the way, as always in Grasshopper, it isolates and detects what are the vertices, the corners, not the vertices, sorry, the corners of the given mesh. Okay, so once we have them, we can simply convert them into anchor points using the goals point that we already know. Okay, so that's it. We have everything set. I will turn the preview off for all of these things here, and I will use the standard method of applying a false start toggle, a reset button, and then I will start to take corners like anchor points, give the elastic net to the goal objects, and apply gravity to the system. Okay, so now when we reset and release the simulation, this is what happens. Okay, is exactly like with the lines. We have simply converted the initial continuous surface into a discrete system of segments, which is like shatter, of course. And then we have isolated the endpoints or mesh corners in this case and converted into anchor point, gave elastic properties to the mesh with the edge length component, and applied gravities to all the vertices of this system using the vertex loads. So as you can see, it's perfectly symmetrical to the curves case that we already analyzed. One consideration, you can see that even if we started with a mesh that was visualized exactly like a surface or a three-dimensional object with this volumetric shaded preview, Kangaroo is only considering the elastic elements, which are the edges, because as you can see, this component is giving elastic properties to the edges, not to the physical panel or physical polygon of the face of the mesh. Okay, so Kangaroo doesn't care about the panels or the faces of the mesh. It only cares about edges and vertices, which are the particles, by the way. So if we want to visualize the physical or the three-dimensional aspect of our mesh, what we must do in Kangaroo is go into the main group and use the show component. So everything we want to be shown after Kangaroo simulation must be passed to Kangaroo using this show component. And we want to see how the original mesh is affected by this simulation. So I will take the original mesh, plug it into show component, and connect the show component to the goals object as well. And you can see that here is the mesh appearing once again. Okay, so you see that now the mesh reacts to our deformation. So once we have this deformed system, you see that the bouncy solver, when you release the simulation, has a phase of running, and then it says, let's wait for it, converged. When you see converge, it means that this component is no longer calculating. Okay, so it has reached the equilibrium status between all the forces that are acting on the system, and then you can simply switch the toggle to false. The bouncy solver is paused in this moment, so the output system is not changing anymore. Okay, so what do we need here considering this system? If we want to analyze the system, eventually we can work with the edges and vertices and physical elements that we have considered during the simulation. But if we want to build this, for example, we must also work with the mesh panels or mesh polygons, okay, or the faces of our mesh object. So all these things here are inside the output, Kangaroo output. Okay, so you will see that there is a mixed set of objects here. There is the mesh, which is which was passed to the bouncy solver via the show component. Okay, then there are some null objects. Then there are lines, and these lines here are the springs. Okay, so you can see that you have here from 5 to 64, so they are basically 60 springs. You can see that if we take a mesh edges component here, it is saying that we have 20 naked edges, which are the exterior edges, and we have 40 interior edges. So 20 plus 40 is 60, and here you have the 60 springs that are considered during the simulation. And then there are other null, and so on. Okay, so first thing we must do is get rid of the null object, because anything that you might want to do after the Kangaroo simulation could be affected by the null objects. So in order to do this, I normally use a clean tree, and I pass all this data here to the T, which is the tree. And here you can decide what actions you want to perform. Normally, the remove nulls is set to true by default. Okay, so if we take a look at the output of this, you see that there is no longer null objects. There are no longer null objects inside this list of values. Okay, so you have a mixed set here of data with meshes and lines. Okay. Normally, if I want to work with the edges, or I want to work with the mesh, what I do is take, for example, let's say that I want to work with a mesh. I take a mesh container. Being a mesh container, this component here can only recognize meshes. So when we pass this mixed set of mesh, null object, and lines, this thing here can only understand meshes. So when it gets a mesh, he will recognize the mesh. When it gets a null, it will understand null. And when it gets a line, it will convert this object in this line into a null as well. So if I take this and plug it into this panel, you see that there is the mesh, the null object, and all is null here. All but the mesh. So if I clean this data set here, as a result, I only get the clean data, which is the mesh object. Okay? And if I want to work with the edges or with the springs or the lines, I do the same. I take a line container and pass this output to the clean tree, and I only get lines here. So I get rid of the mesh and of the null object in one single step. So whatever you want to use from the kangaroo output, I do recommend that you take the correspondent geometry container and use a clean tree in order to clean the data set. Okay, so want the mesh? Here's the mesh. Want the lines? Here are the lines. Now, where are the particles? The particles are here. They are the vertices. Okay, so if you want to work with the particles, you just have to take a point container if you want things to be more clear, and here you have your particles. Okay, so if you do this, you see that here are your particles moving during the simulation. Here are the lines, as you can see, and if I plug this here, you can see this is the mesh. Okay, so I have clean data coming from the output via this simple data manipulation with the clean tree component. Okay, let's stop the simulation, and we have this object here. Now, there are two problems. Well, first of all, let's see this the same definition with a more complex scenario. Okay, so let's keep this here a while. Well, actually, there is no need to turn it off because we will be using exactly this one. I'm just turning off the preview of the clean tree. Okay, so what I'm going to do now, I'm going to create a mesh system here in Rhino, and I want to use it as to build a compression structure or a catenary pavilion here in Grasshopper using Kangaroo. So what I'm going to do now, I'm going into the mesh menu here, and going to the polygon mesh primitives and take 3D face. Okay, I will create a series of quad faces. Just remember, when you create a mesh or a 4 vertices surface, remember to click on the corners counterclockwise. Okay, so in this case I will click lower left, lower right, upper right, and upper left corner. Since Rhino 6, you are able to create n-agons in this interface, but I do not recommend that you work with meshes with polygons with more than 4 sides or 4 edges and 4 vertices. So just click enter right here, and here you see that we have created a mesh polygon, which is a quad. Now, if I create this polygon like counterclockwise, like this, I get this object here. If I create the same polygon clockwise, so like here, 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 and here, you see that this comes out orange. Why? Because in my interface, orange represents the negative face of the surfaces and meshes. Okay, so this was created counterclockwise, and its positive face, its positive normal is pointing upward, and this was created clockwise, and its positive normal direction is pointing downwards. Of course, if I take a look at this from the bottom, you see that things are inverted. Okay, but anyway, I want to create meshes counterclockwise. Okay, so just follow this this thing, and I want to create other quads which are joined to this one. Okay, so I will create other 3D faces, and just keep in mind that if you want to snap to this vertex here, this is a vertex, it is not an endpoint. Okay, so if you don't activate the vertex snap, you cannot snap to this endpoint here. So activate the vertex, which are mesh vertices, and then counterclockwise create another polygon, and then another one, and then another one, always counterclockwise. And you can add as many polygons as you please. I will just stop right now. Okay. Now keep in mind that these are 3D faces mesh primitives, so they are independent meshes. So if I select all of these, I will be selecting 6 different meshes, even if they are touching each other along edges. So I must select them and join them. Okay, so 6 meshes joined into one open mesh. Now this is one single mesh, and I will take a mesh container in Grasshopper and right click and set one mesh. And you can see that here we have our mesh imported. Okay, I will internalize this data here and get rid of the original mesh in Rhino. Now what I want to do, I want to use this mesh as initial system instead of this one. So what happens if I simply move all these cables here from the mesh surface to this mesh? Well, I can drag all these cables with Control Shift and dragging the cables to the new mesh. Okay, and I can visualize the clean tree result, reset the simulation, and turn it on. And you see that this object here is behaving weirdly. Okay, why we get this strange deformation? Why we see this object is not bending? Because this mesh is made up of 6 faces. Okay, while our initial plane surface was divided into a more dense network of polygons made up of 5 by 5 polygons. They were all free to move. They were only anchored at the 4 corners. Okay, where are the anchor points of this mesh? They are here. These are all corners for the mesh corners. Therefore, this whole object is anchored to the ground, like here, 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 and all these vertices here are being kept anchored to the ground. So there is almost no possibility for this object to leave the ground, and also there is no possibility for these edges to bend because they are just one single ideal spring each. Okay, so in this case, if you want to work with this, I would recommend eventually that you actually, let me recover the original. Okay, this is the original situation. What I'm going to do, I'm going to take this mesh object, and now yes, I need to use the old Kangaroo 099 mesh utility, which is called quad divide. Okay, of course there are other methods, but I also want to give you an idea of the utility of these tools that were discontinued with Kangaroo 2. Okay, so I will add this object to this group, and I will take the original mesh and use the quad divide to do this. Each quad of the original mesh is being divided into quads using a 5 by 5 subdivision. So each of these quads, which were 6, is being divided into 25 quads. And so we have one mesh with 150 polygons here, quads. So this is actually the mesh that we are going to use in our simulation. I will take basically these cables here, Control Shift, and drag them to the quad divide output. Okay, and now let's take a look at what happens with this. We must reset the simulation, of course, as always, and then run the simulation. And you see that this thing is behaving properly right now. Okay, so we have a much more interesting object from an architectural point of view. And the whole object is actually working only with tension, let's say so, because it is falling upward. But you must imagine that this object, once you freeze it like this, it's capable of resisting to compression coming from the top. Okay, so these are not arches; these are catenary curves. All in this pavilion is catenary. Okay, so you can take these and eventually bake it as it is, and you have this pavilion ready for being built. And so this is the pavilion, or the shape that we are going to use right now. Now there are two problems that we must discuss in order to bring this object to real life. First of all, the fact that if we consider, for example, the original mesh, the system before the deformation, you see that all these faces here are quad polygon, so they are basically made up of 4 sides, and they are flat. Okay, so this object here, if you want to produce these panels here, it's very simple. You can simply cut them using whatever type of cut technology you might want to use. Okay, but when you apply gravity to this object, and this object starts to fall down, well, down, up, or deform in general, okay, there is no guarantee that these quads remain flat. Okay, so in order for these quads to remain flat, the only possibility is that the 4 vertices lie on the same plane. Okay, but this is basically impossible. So if you take a look at any of these polygons here, let me switch to wireframe preview. Any of these polygons will have some distortion. So for example, let's take this one here. You see that there is no way to align these 2 vertices with these 2 vertices here. Okay, you always have some kind of deviation between the edges of these quads. So it means that these quads are not flat. So how can we produce this kind of structure? Because the risk is that in order to produce each of these panels here, you must use expensive technologies or expensive processes. So what we want to do is convert this object here into a surface, let's call it so, or a system made up only of flat surfaces. Now there are 2 approaches to this. Kangaroo can try to flatten the panels. Okay, so if you go into Kangaroo goals and goals mesh, you would see that there is a component that is called planarize. Okay, now you can try to work with this and see what happens, but planarize is another goal, so it's another force. Okay, you know that catenary curves, as we have discussed, are generated by only considering elastic properties of the material and gravity, and eventually applied loads. Okay, planarize is a force that tends to maintain a polygon, a quad, flat. So it acts despite the gravity action and despite the elastic properties of the material. So eventually, if you work with planarized component, what happens is that the shape that you get is no longer a catenary shape. So basically, this will not be a compression-only structure. So if you exaggerate with the planarized component, it means that this object that seems to be identical to the original one will simply crumble if you try to assemble it in a real world. Okay, so I would not recommend to work with planarize unless you are able to adopt some security measures when you use this. One safe method is to take the output and convert it into eventually planar surfaces or planar panels. Okay, so let's say that we have this output here from the clean tree, which is a mesh with 150 polygons, 150 quads. Okay, so what I want to do now, I want to analyze if these quads are flat or not, and how much flat or how much non-flat they are. Okay, so in order to do this, once again I switch to Kangaroo 099 and take one component, which is this thing here, planarity display. Now this is a component that allows to visualize if a quad is flat or not, is planar or not. Okay, so what I'm going to do here, I'm going to take this mesh, plug it here, and you see that this thing here is performing an operation which is actually not visible by default. You have to work with the output of this thing here. Now let's try to understand how this planarity display component works. I will simply, let me just organize things a little. Okay, so we have planarity display. Planarity display is saying, okay, give me the mesh and tell me what is the base domain. Now what is this base domain? This base domain is saying, tell me what is your acceptable range in which the panel, each panel can be still considered as a flat surface. Okay, so we see that this base domain means from 0 to 0.05 means from 0 to 5% what? Deviation. So considering the flat surface, if the deviation is contained between 0 and 5%, then this component will still consider the quad as a flat panel. Okay, while if the deviation is larger than 5%, then this component will recognize the corresponding panel as non-flat. Okay, now what do we have here as a output? We have a number which represents the deviation. So you see that this panel is basically flat. This is basically flat. This is not flat for just for 0.005 basically. This is absolutely non-flat. Okay, this is a 13% deviation with respect to the planarity condition. Okay, but anyway, you see that this is representative of the planarity of each panel. Okay, so we have a planarity coefficient here. And then we have here 150 meshes, which are each of the quads of our mesh, and we have 150 colors representing the planarity of the mesh. So we can also do something like this. We can take a custom preview, take the meshes here, and visualize them, each one with its color. So whenever you see green, light green, or orange, etc., you are seeing basically panels which are almost flat. Of course, green means that it's basically flat, okay, which are basically these ones here. But when you start to see 0.03, it means that you're already getting into the orange zone, okay? When you see red, it means that you have at least 5% deviation or more. So everything above 0.05%, it means that its deviation with respect to the planarity condition is larger than 5%. Of course, you can decide, for example, what is your limit for planarity. For example, you can set this value to any value between 0 and 1, where 0 means 0% tolerance and 1 means 100% tolerance. Okay, so if I set this to 1 and plug it into I, you see that everything turns into green or greenish. Okay, so everything is basically flat here. But if I start to decrease this, you see that reddish panels start to appear. So if I say, for example, 0.5, these panels here are the panels that have 50% deviation with respect to the planar configuration. Okay, so let's say, how do I determine this value here? Well, basically, you have to understand that if you have a structure like this, there will be frames and panels, okay, normally, unless you are building this only using three-dimensional bricks, let's call them so, okay. But if you have a frame, in case you have frame, for example, the frame will have some height. I will represent it like with a eye profile here. And therefore, if you have two profiles here, when you have a panel which has some deviation, you might have a panel that does something like this, and then it runs up, and it runs up, and it does like this. So you have some kind of distorted panel, but this distortion, this deformation can be absorbed by the height of these beams, basically. So you can easily define what's the maximum deviation that is acceptable, because if you planarize the correspondent panel, you are sure that the frame will be able to compensate the deformation that you are creating. Okay, so that's why you determine what kind of deviation, maximum deviation, you are ready to accept in your simulation. Okay, so let's say I will use a 25% deviation limit. Okay, so everything that is red is something that, for example, I cannot simply produce these panels here, this red panel, using a cut technology. Okay, so because they are not flat. And what I want to do, I want to let's say keep the cost under control, so I want to use only cut technologies, like for example glass panels. Okay, so in order to do this, what I need to do is I can let's say leave the greenish panels as they are and take into account only the red ones. Now the red ones have a deviation which is at least 0.25. So if I take these numbers here and understand which is larger than this deviation factor, then this will give me a sequence of true false. If I want to include 25%, I will use the larger than or equal to. Okay, so if I do this, let's find a value which is larger than 25, like 33. Value 33 is 0.31, and then we have a bunch here. Okay, so if I take this panel here and plug the larger than and equal to, you see that 33 correspond to true, and then there are this bunch of values here which are all true, 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 and so on. Okay, so when we have problematic panels, this will return a true. Okay, so if I dispatch all the panels here using this pattern, in A I will have the problematic panels because they correspond to true, and in B I will have the, let's say, acceptable panels. So what I'm going to do, I'm going to take the problematic panels and I'm going to use a triangulate component. So I will take these problematic panels here and will split them into triangles. Why? Because triangular panels will always be flat. Okay, so if I take a mesh container and plug the new triangulated panels and the acceptable quads, now what I have is a mesh which is made up basically of flat panels, be them quads or triangles, it doesn't matter, but I am optimizing the presence of triangular panels according to the maximum deviation that I can accept in my project. So if I decrease this, I will have more triangles, of course, but if I am capable of considering more deviation, then I will have less triangles. It depends on the frames that I will be using. Okay, so if I return this to 0.25, it's nice to see, for example, how this simulation, or how this, let's see it from the top viewport, these triangular panels start to appear according with the deformation that occurs over this mesh. Okay, so this is the first consideration. So we have here a set of made up only of let's wait for this to converge, only of flat panels which are ready for production. And of course you can use any technique for let's say name these panels and put them on the floor, basically on the ground here, and prepare them for cut technology or cut processes. Okay, and bring them to production. Second observation, let's say that we want to exactly to produce this. One thing is to let's say cut each panel and then assemble this structure piece by piece. So we will have, in this case, if you take a look at this, well, actually, if I join using a Weaverbird's join meshes and weld component, if I do this, I see that I have a mesh with 196 pieces, okay? So I have to produce basically 200 panels and then assemble them one by one, paying attention to the shape and position and unions and joinings that I have to create here. Now, there is another approach. Basically, we can use a different technique, a different approach, where we split this object into chunks. And each chunks can be cut and then put into place by simply folding along the edges. Okay. So, for example, imagine that I am able to isolate all these stripe here of panels. Of course, I can develop this stripe flat on the floor, on the ground, and then I can cut it and simply bend the panels, fold the panel using a specific angle along each of these edges here. Okay, so this is what we will try to do now. I don't know if we will succeed. Let's see, because normally this operation is quite complex. But in order to do this, there is a plugin, a Grasshopper plugin, which is very important. And it's also, let's say, one of the scary plugins because it's quite complex, but it is called Ivy. Okay, and Ivy is a plugin that allows to create a, let's say, topological interpretation of the mesh structure in order to unfold it and to develop it flat on a plane and be able, therefore, to easily manufacture this object. Now, let's take a look at Ivy and let's see how it works. Okay, so what we're going to do right now is take this mesh that we finally obtained by kangaroo simulation, and remember that we triangulated some panels, but some panels are still quads. Okay, what we're going to do is going to use Ivy for Grasshopper. Now, Ivy is a plugin that allows to basically deconstruct the mesh structure and create some kind of connection between edges and polygons, and use this rule that is created all over the mesh in order to create mesh chunks and unfold these mesh chunks into flat mesh parts that can be easily manufactured and assembled in the real world. Okay. Now, Ivy is let's say quite complex as a plugin. Because it is based on a very peculiar algorithm that you can see here in this group that is called primary segmentation. Okay, so you find this kind of strange names like DFS, MSD, and so on, and you see these like names which are somehow non-easily understandable. Okay, but they are all algorithms that allow a particular segmentation of the mesh. So you see that there is a number in this group. This is basically the sequence in which you want to create the workflow using Ivy. Now, I have prepared here a whole definition where you have the kangaroo simulation and also the Ivy part for unfolding the mesh flat on the ground floor, basically. But I will apply this the same Ivy definition. I will not write it from scratch because it is quite boring and complex. Okay, but we will serve the existing one. It's absolutely irrelevant if we build it from scratch or not. But I will go through each and every step of this definition. So let me just unplug and disconnect this cable here and reactivate this. Of course, this definition is disconnected, so that's why everything is orange or red. Okay, so let's see what happens when we have this mesh here and we plug it into the triangulate. You see that this is actually the result of the IV operation that are made in this area. Now let's see what happens. Let's see how it works. Okay, so I will turn everything off here, and we go back to our initial mesh. Now, IV needs to work with triangular polygons. Okay, so what I do here is actually triangulate the whole mesh. So all the work that we made in order to optimize the shape of the panels in order to have all flat panels, here it becomes absolutely irrelevant, as you can see, because we must triangulate. And also there is this weaver joint meshes as well, because this part of the definition was used in another definition where the meshes here were basically derived from here, from this planarity display. So that's why you see that there is this additional weaver joints and mesh joins and join and weld, but here you already have an idea of how you should manipulate the mesh after the kangaroo simulation. But this method works for any mesh. Okay, so you can unroll and unfold any mesh that you might want to use. So once you have one single mesh, the first thing you do is create a mesh graph. Okay, so the mesh graph, you see that there are several components here. Now this is the first one that you want to use. So you have one mesh actually, and you want to build a graph from an existing mesh. Okay, so this component here, what it does is create connections between adjacent polygons. Okay, so you can see that, for example, here this graph from mesh determines which is the center of any any polygons along the mesh, and then create this connection here between the centers. Now this is in some processes this is called the dual connections. Okay, so the connections between all the centers of the mesh polygons. But you can see that these connections here touch the middle point, the midpoint of the edge between two centers. Okay, so it is not a straight line. Okay, so this is the graph from mesh. So you see that this graph is actually connecting all the center point of all the polygons of the mesh. Okay, now the important thing is the following step. The following step is a weight graph. Now what does this component do is create let's say preferential connections between the center. Inside this graph that the graph from mesh creates all over the mesh, this face angle edge weight, which is the component that I am using in this case. There are several components, several functions here. You can decide whatever you might want to use, but in this case what I want to prefer as a criterion is to let's say identify those connections that are determined by the angle between two faces, two adjacent faces. Okay, so what happens when we do this? This component here starts to run through the graph that we have created, and it starts to give weight to edges along the mesh according to the inclination of two adjacent faces that connect along the edge that we are considering. Okay, so for example, what happens here is that take this edge here. This edge connects this face and this face, and this is the line that connects the two faces, adjacent faces. Okay, and according to the inclination between this face and this face, this edge here will be given a weight. Okay, so this is the meaning of this component here. So once you have given a weight to all the edges of the mesh, you can use a primary segmentation, which is basically the algorithm that, according to the weight that the face angle edge weight gives to the graph derived from a mesh, this is actually creating selective paths according to the weight that this component gave to the edges. So this will create basically these paths here that don't run all over the mesh. They just create preferential paths that are derived from this face angle edge weight. So faces which have let's say an homogeneous inclination, they are all kept connected together by a single branch here, as you can see. And you see that these connections here do not touch let's say do not touch each other. Okay, so you have this kind of branches here. Actually, you might think that the branches run from the part with more thickness to the part which is thin, but actually it's the opposite. These branches run from the thinnest part to the thickest part. And you can see that they are independent branches. So you can see that, for example, not all the branches touch each other. You might have also separated branches. Okay, these branches here are basically determining the chunks of mesh that will be eventually unfolded and unrolled on the ground plane. Okay, so I repeat. First of all, you create the whole graphic. Okay, which is this set of line here, the green line that you see here. Then you decide what method you want to use to separate the graph into several branches according to the weight that you give to the graph, and the weight can be assigned by using different criteria. The criteria that I'm using here is the inclination between two edges and faces. Okay, so then it's basically what I'm trying to do is group faces that have an inclination, an angle which is basically uniform, more or less. Okay, and this algorithm here is creating the relative branches and connection. Okay, so this weight split graph, what it's doing is actually taking the graph created by the MST Kruskal, which is the algorithm for primary segmentation, and it's basically splitting the graph. So each of these branches will be treated apart from the other ones. Okay, so you see that this is actually, you can see that it's basically the same graph as the preview, but you can notice as here you have one single simple cable coming out from the MST Kruskal. So it means it is just one single graph. Okay, but here once you split the graph according to the desired interval that you want to use, then you have a list of graphs. Okay, so you see the same preview, but you have a set of several different graphs. Okay, and so here you have this mesh graph here, which is actually a mesh graph component is like any of these params containers here, but it's capable of containing mesh graphs from Ivy. Okay, and once you have your separated graphs, then you can visually unroll them. Okay, and you can see, for example, that in this case, these are the chunks of graphs created over the surface already unrolled. And you can see that here you have a coefficient here for unrolling. Here is set to 1, which means complete unroll. You can see that they lie flat, each one with its own inclination, which depends from the starting phase that you want to consider for over the mesh. But you can also set this to, for example, 0 in order to see the whole process. Let me hide this. And let me also hide the original mesh. Okay, so you can see these are the graphs that are going to be unrolled. Okay, and they correspond exactly to this mesh graph here. So once you have this mesh graph visual unroll, you can simply drag this, and you see that here you have the branches that are being unrolled up to 100%. Okay, so they all lie flat here. And you see that this is receiving 7 values, and you might recognize that here you have one flat chunk, then you have this one, and then you have this one here, and then you have this one here. Each of these frames that you see here represents or identify one of the 7 graphs that we are rolling. And then what I did here was eventually a very basic operation for taking all the unrolled graphs, okay, and then I just place them inside a grid on the XY plane. So you can see here you have the graphs unrolled on the flat on the plane. Now this operation here is an operation which not always succeed. It depends on how complex the mesh is. So you might want to tweak parameters here. That's the complex part. Because as you can see, the workflow is pretty straightforward, but there are many problems that can arise. Like for example, this one. Okay, so you see that, for example, this chunk here, when you unfold it completely, there is no possibility for this mesh to avoid self-intersection. Okay, so it means that eventually, once you get this graph here, you might want to split it eventually along this edge here and obtain two separated graphs that you can produce or manufacture into two separate chunks. Now I end up this IV part and also this compression structure final part for this video course at this stage. Okay, so the unfolded and unrolled on the XY plane parts for this mesh. But you see that there are also some fabrication components here that allow to place this kind of flaps on the edges of your mesh in order to be able to, for example, prototype this, like doing some rapid prototyping with paper or so on, or something similar. There are also some interesting components here that allow to name, well, actually put numbers to each chunk and each edge along the chunk in order to be able to reconnect to the corresponding edge of a different chunk. But anyway, these are basically easier than the first part of the IV workflow. So I will leave this last implementation to you. And that's it for our video course. I always give the possibility for you to drop me a line in case you need some further explanation, or you have any doubt regarding what we have seen so far during the video course. I also do recommend that you subscribe to my YouTube channel, and you also add me to your social networks. I'm very active on social network. I will give you here in this file. I will also give you the my nickname. You can find me as JankADM. JankADM it's my nickname in on Facebook, on Twitter, on Instagram. It's always the same, so you can easily find me online. Here you have my website, so you can stay updated with new video courses and tutorial and news. Okay, so that's it for this video course. I hope you enjoyed it, and bye.